Hey, how y'all doing?
Good.
Woo. Okay, so where we stand is one more topic to go in theory before well, tomorrow we're going to be going over sample final exam so that way you feel ready to tackle the problems on the final exam. And again, your final exam will open as of 5 p.m. on Thursday. And as long as you get it done by 11:59 p.m. on Friday, all's good. And if there's something else that's I need to be aware of, let me know. Sometimes that's a good thing to let me know in advance. Because sometimes people are traveling or for whatever reason get sick. Yeah, don't be hesitant to let me know what is going on where you're at. If there's something that I need to be aware of, it's better for me to know that. Okay, so with all that in mind, I am happy to tackle administrative issues that you might have, if any, before we finish it up with one last topic.
Is this stuff going to be on the final?
Yes, anything today is valid for the final exam. And you're thinking, crap, that's really close to the final exam. Well, you could take the final exam on Friday instead of on Thursday. And in class on Friday or Thursday, you could definitely ask about anything related to class today, the lab activity associated with class today. And so that's probably a good thing. Second, the topic today will, with one minor exception, look really familiar. And because we're casting all of today's topic in terms of, oh, it's just a regression, you know all of the regression tools. It's just that there's a subtle difference in today's version of regression, logistic regression, than in the ones we've fit so far. So yes, it's timed importantly to sort of be, if there has to be like one thing at the very end, like yesterday and today, the content shouldn't be like big deals. It should be rather, okay, yeah, we sort of know that. We feel comfortable with that. It's reviewing a couple concepts that you know in a slightly new context. That's the hope. So I'm hoping that answered your question, Kendall. You were nodding, so I'm just assuming. Anyone else? Okay, what I'd love to do is to start in on that newish content then by displaying, well, what I normally do, share screen, and which one? How about that one? Okay. So really today we're dealing with categorical response variable. And here's a simple example that comes up in Stat 218 when I teach it. There's a medication out there called Xenical. It's an orlistat. It's in the family of chemicals that sort of clomb onto a fat cell while it's in your stomach or your intestines somewhere. And it basically, between this chunk of plastic attached to the fat cell's too big to be absorbed through the stomach lining. And so it's eliminated from the body via natural process, which is euphemistically, yeah, you crap it out. And if you've got a bunch of extra fat in your, as it cruises through your lower GI tract, it might change the nature of what happens at the end of that GI tract experience. And when considering approving this medication, the FDA asked for this company to evaluate whether it impacts the rate of, well, euphemistically, we could call it fecal urgency. But in plain English, you ask these people, you don't ask them, hey, did you experience fecal urgency while you were on the chemical or, and this controlled drug trial? You ask them, have you had explosive diarrhea in the last 3 months? And so we have about 3,300 people, tossed about 2,000 of them into the Xenical taking group and 1,500 into the placebo group. and they took the medication for a period of 3 months before we asked them these initial questions on a variety of possible side effects. And in the Xenical taking group, about 350 of 2,000 experienced this side effect. That's a high rate of this side effect. Only 98 people out of the 1,500 in the placebo group experienced that side effect. Okay. The response variable is yes or no. Yes, I had fecal urgency. No, I didn't. It's one or the other. Okay. In a situation like this, or even if we have quantitative explanatory variables, we could use what we term logistic regression to tackle the problem. Okay. And so what we're doing is coming up with a regression, and everything on the right-hand side looks familiar. There's an intercept and the slope times x1 and a slope times x2. And heck, if you have quantitative variables, that's all familiar. If you have categorical variables, you can either use the reference group parameterization or the sum to zero parameterization, like we talked about earlier. And that could be, the effect of it being someone who is male versus female. That could impact the chance of fecal urgency. Okay. But on the left-hand side, instead of y, we're looking at the natural log of the ratio of the chance of fecal urgency over the chance that you don't have it. If P is the chance of fecal urgency, 1 minus that is the chance that you don't have it. The log of, if you will, the odds of fecal urgency. So if you bumped into, in a past stat class, the odds, that's a chance of success over the chance that you have a failure. Log of the odds is what we are modeling. And if if you want to convert back to the value p hat as a function of these slopes and the intercept and then the x values, p hat is e to the sum of all of those things, if you will, e to the log odds. This literally is the log odds. If we have an estimate of that log odds, e to the estimated log odds over 1 plus e to the estimated log odds. Or if you like to simplify your life algebraically, you could go with 1 over e, 1 plus e to the negative of all that. I prefer this top version, and I think many students do as well. But if you're doing it by hand, this might be quicker. Certainly, I'd definitely practice and confirm that you get the same answer both ways if you're going to start to prefer the second formulation. So far, so good? Yeah, it's just this new y, the log of the ratio of success to failure, is a function, a linear function of your x variables. So I wanted to look at a couple examples. One of them is, well, with our Xenical example, Xenical and our fecal urgency. And let's see if I got the data here. There we go. I've got these data, and they're listed in sort of a funky way. Xenical Y or N for yes or no. Fecal urgency, or FU, if you want to call it that, abbreviate, yes or no. The outcome is yes, you did, no, you didn't. And this count is the number of individuals in each of these different contingencies. Some would even call this a contingency table. So 356 FU X, X FU 356, 1557, no fecal urgency in Xenical. So on the FU N, no, and then Xenical, yes. 98, yes, 1368. So these counts basically tell me how many of these are there in each of these four groups. Okay. So let's go after what GMP does for us when we choose to model this categorical response variable of FU. So if I were to do analyze fit model, and this is the way I'm going to approach it, analyze fit model, boom. FU depends on whether you're taking Xenical or not. And remember, this count data contains, how many people are in each of the different categories. So I'm going to put it in here as the frequency. How often do we have each of these four situations, each of these four possibilities. And I'm going to hit, I'm going to note here that when I dragged FU into here, the personality became, instead of our earlier least squares, standard least squares, or stepwise, it became this thing here called nominal logistic regression. If you have two different values for your response variable and they're identified as in a categorical response, you're going to get a nominal logistic. If you got three or more variables, it's going to be a little bit different. Okay. But, that's what you get. Three or more variables, it's just a hair different. So nominal logistic, and I'm going to hit run here, and I'm pretty sure it's going to complain at me. Damn it, it complained at me. So yeah, cannot decrease objective function, fine, just ignore it, continue anyway. So that's something I don't like to have to do, is to say, okay, override the computer telling me there's a problem here. I did verify, and this is something with GMT17 with this data set, but not in 16 and earlier. I did verify that the results are exactly the same as in 16 and exactly the same as another algebraically equivalent analysis to this logistic regression. So I feel pretty good about saying, just go ahead and do the FU. Stuff to look at. Oh, here's a whole model test. Oh, F for the regression across the whole model. Is at least one of my variables helpful? Yes, that is the case. Okay, we get something called an R squared. Well, okay, we've defined R square as corresponding to the percent of variability of the response variable numerically that could be considered explained by X's. That's not exactly R squared here, but there is the equivalent of an R squared value. Okay, and this says 0.0407. That doesn't seem large, but it still might be statistically noticeable because of the large sample sizes. Okay. This effects likelihood ratio test, that's where you're going to find something like the effects test that we had done earlier. And our parameter estimates, there's an intercept, yay, and then an estimate of it being Zenecal. Zenecal at the no level takes that, if you will, intercept and lowers it by 0.58. Because we have a sum to zero style in this class, if you take that intercept of negative 2.06 and add 0.58, again, that's going to be the logical algebraic opposite, or I guess additive opposite of Zenecal no, would be the Zenecal yes effect, is to add a 0.58. That would give you the numbers we could plug into this equation. And the claim is e to the negative 2.05586, etc., over 1 plus all that good stuff should be equal to the chance of fecal urgency in each of these two groups. Now I'm going to show you in something that's the equivalent for me of this. And can I make this bigger? Yes, I can. Okay. So I'm going to sort of show you in this, maybe make it even bigger so it's easier to read. I'm going to sort of work in this package called R. It's essentially like a calculator that can do additionally some statistical analyses. I'm not going to use any of the statistical analyses. I'm going to create something called the log of the odds. That's just negative 2.0558615. Okay. Plus then negative 0.58 02761. Okay, that would be the log of the odds if you're in the no Zenecal group. And so I'm going to say all I need is to know I've got B0 plus B1, well, times X. We're in the Zenecal group. This is A. an effect of being in the Z alkyl group. So e to the this over 1 plus e to that should give me the chance of fecal urgency in that no Z alkyl group. So exp e to the power of the log odds over 1 plus exp of the log odds. Okay, so 0.0668, yeah. So 6.68% of individuals in the Z-alkyl group are experiencing fecal urgency. What about the log of the odds of that other group? Well, the log of the odds in that other group is, instead of plus a negative, we're adding the numeric opposite, I guess additive opposite. So the log of the odds now over e to the log odds over 1 plus e to the log odds, that tells me 18.61% of the folks in the Z-alkyl taking group are experiencing this thing called fecal urgency. So we have rate of a failure. Rate of success in the control group, rate of the success in the treatment group. And fecal urgency probably shouldn't be called a success. I'm just going to say it's one of the two outcomes in question. Let's show you how to get these exact same two numbers inside a JMP. You could do it by hand, or like I use a software tool to do it, but it essentially was a calculator. Here we have our friendly turn on or off some options. A save probability formula. Okay, that sounds promising. Tell me those chances. And that should tell you for each of these 4 different cases. Okay, I'm starting out 4 cases for each of the 2 different treatments. Okay, so there's the Z-alkyl taking, that's the top 2 rows. We're saying the chance is 18.61%, which is what we just said. But in the in the not Z-alkyl group, the placebo group, what we're spotting is a 6.68% of the folks have fecal urgency. And so our fitted model tells us the chance of a success in each of these 2 cases. So far, so good? Okay. So let's talk about not just some medication which is used for weight loss. Let's talk about a different story. And y'all remember the 4th grade. Some of you remember it better than others. But do you remember in 4th grade where you had to do your project on California history? And okay, so not every one of you is a California resident when you were in the 4th grade, but if you were, and in public schools, you probably built a mission out of sugar cubes or something like that. Yeah. No one ever does class projects in 4th grade on the Donner Party, but if you look it up in Wikipedia, yes, you can find out about the Donner Party. And I'm not sure, did I put that in the lab? I don't think I did the Donner Party in the lab. Let me just verify. That would be really awkward. No, for the lab, we've got the Titanic instead of the Donner Party. So clearly this is disaster day. Okay. So the Donner Party, these folks left St. Louis in late March, early April to head west with covered wagons and whatnot. Donner was the name of not the trail guide, but rather the family that was the biggest family in the group that was traveling together. And the trail guide said, well, you know, leaving late's a bit of a problem, but, you know, you can risk it. And they're like, yeah, let's do it. And they leave St. Louis, heading west. They cross the Rockies. They cross the San Juan Mountains. They travel across a desert. Somehow they get to Reno, Nevada, as it's starting to snow. And they said, we think it's a good idea to head west and cross the mountain in that gap that we now call Interstate 80. And they got a few miles and it started snowing more heavily. And they camped out at this cabin that they found right near what's the name of the town? Truckee, right near Truckee, and right near Donner Lake in Truckee. And we all know from the story, or we could look up Donner Party. We could look it up on Wikipedia and find out that maybe it was a big mistake to leave that late. Some of the people died, some of the people survived. The outcomes are died or survived, and we could model the chance of death as a function of, say, the sex of the person in the party, or we could say the chance of survival is a function of the sex of the person. Either way you want to go, we're going to create a model under Analyze Fit Model, like we've been doing for a while. The outcome, did y'all spot that? Under Analyze Fit Model. Once I said the outcome, I notice the personality, there is no personality. But if you say the outcome is categorical and 2 levels, it says, oh, you want logistic regression. I'm assuming JMP says that you're going to want something in particular. If you want something else, you can probably come up with a way of reformulating this. JMP is more flexible than the standard least squares that we've been using most of the term. Nominal logistic for 1 zeros, yeses and nos. Well, sex may impact the chance of survival. Does sex impact the chance that you would survive an experience like the Donner Party experience? I'm going to hit run. And my nominal logistic regression says, whole model test, F for the regression. Yes, there is a relationship between whether the member of the Donner Party is male or female and their chance of survival. The likelihood ratio test, that's sort of like an effects test, adjusted sums of squares. That says, yeah, we think that there is a relationship. Our explanatory variable is related to the response. Boom. There we go. Your parameter estimates, the same deal. There's an intercept, and then there is a slope, if you will. That slope, or the effect of being female on your chance of survival, is to take that intercept of 0-ish. And if you're female, you add a 0.693 to 0 to get the log of the odds. If you're male, you subtract a 0.693 from 0 to get the log of the odds. And all we need to do is to push it through the equation. Here's the log of the odds. There's the odds, log of the odds. We know this value for everybody. So e to the that over 1 plus e to that should be something we can calculate. And let's show you that. The Donner Party. So like before, all I got to do is say, oh, I want to save something. And rather than saving my y hat, we don't have a y hat. We have a p hat, an estimated chance of survival, or perhaps the estimated chance of death. We get both provided to us for free, okay? But this log of the odds of survival, or the linear predictor of the log odds, it's a value of negative 0.693 for the males, positive 0.693 for the females, which is the chance of survival of the males of 1 in 3. 2 in 3 is the chance of survival for the females. Chance of death for the males is 2 in 3. 1 in 3 is the chance of death for a female. So we've got our model here. Any questions on whether you think sex has anything to do with survival in a situation like the Donner Party faced? So you're saying, hey, Steve, you just showed me something where you have a categorical predictor. What about when the predictors are quantitative in nature? Well, our approach will still work just the same. I'm going to remove these guys over here just because, fine. Darn it. There we go. Boom. So let's now use age as a predictor of the outcome. We could do that model as well. I mean, our word equation says death equals age. Why not? Let's see how much age impacts the chance of survival or the chance of death. Oh, fit model. And again, like before, the outcome impacts the personality, becomes logistic regression. And we're saying, well, there's a quantitative predictor of age. We toss it in there. Does age impact the chance of survival, the chance of death? Here, we see a bit more output given to us. Okay. So there's two outcomes. There's survival and death, and the chance of survival seems to go down as the age gets higher. Are dead people right up here? Okay, surviving people over here. They are spread out vertically, okay, in a way to sort of make it easier to read, perhaps. I don't really love that way of spreading out vertically. I view the people as right along the x-axis, or right along the, right along the x-axis, or right along the y=1 location. But you can say, well, as we hit higher numbers, do we have more folks who are in this upper category than in the lower category? Yeah, we seem to. However, for the lower ages, more people are in the lower than in the upper category. So this is an attempt to show for each individual the chance of death and whether they actually died or not. So here's a sort of curve that is implied by the log of the odds. Yeah, e to the something over 1 plus e to the something. It's going to have that sinusoidal shape. Okay, so let's find that again. Show all those. Yeah, so it's going to have that sinusoidal shape that indeed we have our variable of age. Does it explain something? It explains something. Our null hypothesis of no relationship is rejected. We believe that age is related in some way to the response. Our parameter estimate, our slope, same p-value. The effects test, same p-value, not surprising. Which one's better? Yeah, R squared of like 7 versus 9. 9's a little bit better than 7. Age does a little bit better than sex at predicting the chance of survival. Okay. Any questions about that so far? I guess what I could do is under our friend here, we could say I would like to save again those probabilities. And this is the probability of survival shown here as a function of just the age. Probability of death as a function of just the age. And the log of the odds of survival, well, that's just a linear predictor. Again, we push it through the e to this over 1 plus e to that. Let's go ahead and plot the chance of survival against the ages. And Graph Builder should allow us to do that. Okay, so age along the x-axis, the chance of survival. Well, there's survival and death. And those are the two options. Notice that it sort of tells you probably of outcome 2 of 0. Well, which one do you want? Let's have the odds of survival on the y-axis. And we can see that as age gets higher, the chance of survival drops. Good so far? Yay. Okay. What about a model then? Because age explains something and sex explains something. Why don't we put them both into that analysis to predict then survival or not? And maybe I should get rid of those guys. And under analyze fit model, I could say, well, outcome, again, outcome, success, or survived or dead. It makes it a nominal logistic regression. And age did a little bit better than sex, but I'll put it in first. Does it matter? Probably not. Effects tests, it doesn't matter. So here is what I've got going for me. First off, we've got now these parameter estimates and a whole model test. Let's look at the whole model test. Is at least one of my two variables helping me? Yes. Our effects test, sort of like an adjusted sums of squares, we interpret the following way. Controlling for sex, does age help me explain the chance of death? And yes, it seems to. Within the ages, is there, I guess across the age levels, is there a different chance, and increasing age reduces the chance of survival? We see that now. Considering there may be a possible age relationship with the chance of survival, is there a difference between the two sexes in terms of the chance of survival? Yes, there is. Controlling for the other variable, does this one help us? Yes, it does. Our parameter estimates here have age as a p-value below 0.05, sex a p-value below 0.05. So we conclude that each of them would be related to the response, controlling for the other. Now, some of you might notice, if you're looking carefully, our chi-square from the likelihood ratio test, these 6 and 5, are not the same as the chi-square for age and sex in the parameter estimates. This is the likelihood ratio test. I believe this is a score test. Okay, there's a third option. There's also a walled test. It doesn't really matter which of the three. They usually agree. But if it does matter to you, consult a statistician. And we could talk about, oh, for you, walled is a better procedure than the score test. Fine. You could use the right test. I think likelihood ratio makes sense to me. I would say each of these two variables seems to matter, even having controlled for the other variable already being in our analysis. And like before, we can take our model and say, tell me the estimated chance of survival for each person in our data set. So save that probability formula. So here we have our friends. The 23-year-old dead male, first row. The probability of survival was like 59%. Dude died anyway. Probability of death, well, 54%. Okay. And we could look at every individual in the entire data set, and we know their chance of survival or not. Like before, maybe a plot would be helpful. So the chance of survival, plot that on the y-axis. I'm going to plot that on the y-axis against the ages along the x-axis. And let's ignore that. Check it out. We've got these two distinct groups. I suspect those correspond to the two sexes. I'm going to take sex and drag it over here as an overlay. And we got the blue females and the red males. And now that I put in that curvy line, it seems to nicely describe the relationship that indeed both sexes have a lower chance of survival as the age goes up. Both sexes have a lower chance of survival as the age gets higher. In females, it's always higher than in males, but they follow the same pattern. It might be hard to see this, but these two lines are parallel to each other in one way. If we took the red line and shifted it to the right, it would perfectly overlap the blue line. Or if we took the blue line and shifted it to the left, it would perfectly overlap the red line. In that sense, they are parallel to each other. Instead of showing you your probability to survive here, let's maybe start over. If I showed you the linear chance of survival against the ages and do this separately for each of the two sexes, you'd say, oh, look, parallel. That parallelness in the log of the odds space, the linear predictor space, is why I will call it parallel, even if your actual chance of success doesn't look like it's perfectly parallel across our two different groups here. They're not vertically parallel, they're horizontally shifted from each other. In that sense, they're parallel. Now, some of you are asking to yourself, because we got a few minutes, why should I believe that the sex, I'm sorry, that the effect of age, the slope of age, should be the same regardless of the gender? Maybe the slope could be different between the genders. Yeah, you're right. Maybe it could be. I'm going to go ahead and kill these guys off. And, oh, that was a bad joke. It's the Donner Party data. I'm going to go ahead and kill the columns off is what I meant. Don't mean to sort of offend anyone here. I'm going to fit a model like before. I can hit recall. But if I have sex and age here both highlighted, I could cross them. So I've got a linear term, a categorical variable to raise or lower the intercept of that linear predictor. And this guy should allow the slopes to differ between the two groups. Run. Okay, so is at least one of the variables helpful? Yeah. Do we have parameter estimates? Yeah. Do I have an interaction which is statistically significant? Well, in the likelihood ratio test, barely. In the score test, I don't see it. But we could still, like before, save our probabilities, estimated chance of death for each person in our data set. And this is, again, the B0 plus B1 times age plus B2 times male or B2 times female, plus then the interaction term, which changes the slope of age. Okay. Let's look at these guys. Graph builder. Like before, let's go with our linear predictor as a function of age. And we're going to do that separately for each of the two groups. Oh, look, we see an interaction. A lack of parallelness here says interaction. Okay, now, darn it. Okay, I'm just going to start over. And instead of the linear predictor, how about the chance of survival separately for each of our two separate groups, which means I guess I want to show an overlay here for the M's and the F's. Okay. For the M's and the F's, we see this is our best fitted model that for females, it's a much higher chance of much higher chance of survival above the age of about 35 or so. It's really clearly different, much higher. Males have always a lower chance of survival until we hit maybe the age of 45 or so, in which case we estimate that males are a bit more likely to survive than females. This is what the data are suggesting. So what's new? What's different with logistic regression? The only difference really is our response variable is not anymore an actual quantitative value. You can think about it as your y variable is the log of p over 1 minus p, which is a little goofy, if you will, but you could consider the log of the odds as being something that you would predict, or in other words, there are these relationships between your x's and then the chance of any particular y value. So for the lab today, you get to deal with the Titanic data set. Again, all tragedy Thursdays, no, all tragedy Wednesdays this term. And then a better data set. I don't know what you know about MARC recapture data. If you want to estimate the size of a population, one way to do it is you go out sampling, and some of them, suppose you're sampling fish, and when you catch a fish, you sort of clip its caudal tail or a caudal fin, something where you're going to be able to look at it later and say, okay, yeah, that one we saw 2 weeks ago. You release it and you catch a bunch of fish. In our case, in this creek system or this stream system in Washington, D.C. area, we caught hundreds of eels. We marked them all as having been caught, came back 2 weeks later and caught them yet again, eels. And based on the fraction of eels in the recapture run that were marked and the number of eels that we captured and marked in the capture run, you can estimate the population size. But there seems to be an interesting thing with eels that literally the chance of an eel being caught in electrofishing depends on the size of the eel. For those of you who aren't biomajors who've gone out electrofishing, as part of a data collection exercise, it's sort of a cool thing. Literally, you have a generator in a boat, and you have the one part, I guess. Okay, a generator generates positive and negative, if you will, and off the back of the boat, you have this this thing that just drapes into the water. Let's call that negative. And the person who is capturing the fish perhaps has a positive probe, and if it's in the water, it's forming an electrical field throughout the water. And as a fish crosses that electrical field, like if any of you are morons like me, when you were a kid, you stuck something in a socket and you froze up, your muscles tense up when you are dealing with electricity. These fish that swim across the electrical field, their muscles tighten on the one side of their body, but not the other. And so they turn. And when they turn all the way around, it's the other side of their body that's facing the side of the field where they had been tensing earlier. Oh, and so they swim right towards the dude with the net. So you're electrofishing, and imagine you're a fish in a stream. You live in a quiet stream, no big deal. And somehow this very loud thing comes cruising up your stream. And then there's like these people in boots stomping around and, probing the water. I would hide if I was the fish. The small fish are much more likely to find a rock or a log or a stick or something that will get them out of the way of the electrical field. The larger eels, the larger fish are much less likely able to avoid the electrical field. So I think that the larger the fish is, the more likely it's going to be in the capture run, caught and captured and tagged. And also the more likely it is to be in the recapture run. So part of your lab is dealing with these data and tackling the question, are we more likely to see you as having had a mark on you if we capture you in the recapture run, if you're larger than if you're smaller? Does size impact the chance of capture? And we're going to control for which section of the stream you're in. Because in some parts, some streams, it's like a really wide, big stream, and there are a lot of hiding places because it's a big old stream. Other sections of the stream, way upstream, not so much hiding places. So more likely to be caught or captured in some parts of the stream than in the others. So you get to deal with that data and figure out the relationship between size and chance of capture, having controlled for which section of the stream you're in, much like our Donner Party data here. Any questions before we're done for the content for the term? I guess in lecture content, you still are finishing it up in the context of the lab. Any questions before I turn off the recording? Okay, so I'm going to turn off the recording then, and boom. we'll see you tomorrow. And tomorrow is going over the sample exam. We'll see you soon.